Okay, take 20 more seconds.
We're not even there yet. We're started, yeah.
All right. Right now we have, they're in with their eye clickers. So chime in what your answer is. We've got lots of A's and lots of E's and a few in between. So, oh, you want to see the problem again? Or the solutions? Okay. All right, we're going to walk through this problem. If you've got questions, go ahead and ask. You can also try to contact the TA at the end of the row and have them come down and help you, but we'll go through this together. So first thing, I'm looking at the graph here, and I'm looking at the graph. I have cosine here. Oh, that doesn't work very well. There we go. Okay, I've got cosine of x right here. I've got sine of x. What's an important thing for me to notice about this graph, the graphs here?
On the left-hand side, the cosine is above, and on the right-hand side, the sine.
All right. So since the question asked about area, area cannot be negative. So I actually have to calculate this piece and this piece separately. Okay. They are symmetric. They're not just symmetric, they're congruent. They're exactly the same area. So I actually can just do one of them and double it. If I was in your shoes, I probably wouldn't have known that then, and you might just have to set up two integrals, which is still just fine. Gives you good practice anyway. So let's work on setting up the integral for for the left side. Oops. I wish I had a. There we go. What was my upper function? Cosine of x. What was my lower function? Sine of x. What was my lower bound? Yeah, we go from x equals 0, upper bound, pi fourths. So I'm not doing the whole thing. So I know a lot of you picked one of them, either cosine or sine, minus the other one, and went 0 to pi halves. And if you do that, you'll end up with 0. And there is a context where that makes sense. For example, if these are the rates of two people walking, for example, and they start at the same spot, you would ask how much further is one ahead of the other? They're back at the same spot. So the person at the cosine rate, they're traveling at maybe 1 foot per second to begin with. Sine isn't traveling any. And as they walk, the cosine's going to get ahead. Then the sine's going to eventually catch up to them at the end. And that's the 0, meaning 0 in that context is, hey, one is not ahead of the other. They end up with the same position. But that's not what this question asked. It asked about area, and area cannot be negative. So this, one way to interpret this is that this is the height of my rectangles, or of an arbitrary rectangle, and this is my width. But if I come back up here and think about approximating this area, okay, I can think about the height of this. Ooh, let's change colors. Oh, dang it. Try something fancy and look what happens. Okay, so there we go. So the height of this rectangle, how do I figure out the height? Well, when I plug in an x, I've got an x value down here. When I plug that x value into cosine, it gives me out a number, and that number is this height right there. That's the cosine height for that x, from there up to there. When I plug the x into sine, it gives me a height. It gives me this height right there. That height is sine of x for that x. So what is this distance here? The difference between those two. So if I take the cosine minus the sine, then I should end up with that height that I want. And that same strategy works for any rectangles along here. No, cancel. Okay, if I take, oh, come on, I have to wait for this to catch up. There we go. I can think about lots of little rectangles. And for any of those, the height of those rectangles are the cosine minus the sine, for any of these x values down here. Okay, you might call them different x values. All right, I know you guys probably didn't think about rectangles and chopping it up like into rectangles. You probably just went right to areas under curves or areas between curves. That's okay, although some of the hardest sections that we're going to face, they're hard because students aren't very good at thinking about how to chop up the situation and get the integral form. So I'm going to be emphasizing the chopping up and how we think about it chopped up, because that's going to help us know how to put the form into the integral, what the integrand is. All right, so I'm going to do the 2 times trick. Oops. So let's just do one side, and we'll multiply it by 2. Let me get a different color here. Okay. So antiderivative of cosine of x is sine of x. And then minus, what's the antiderivative of sine of x? Negative cosine of x. And that whole thing is multiplied by 2. And I'm evaluating from 0 to pi fourths. Oops. And so 2 times, what's sine of pi fourths? Square root of 2 over 2. This is minus a negative, so that's going to become plus cosine of pi fourths. Another square root of 2 over 2. 45 degrees, sine's the same as cosine. Minus, then I'm evaluating at 0, so minus 2 times sine of 0 is 0 minus a negative. What's cosine of 0? 1. So don't assume just because your lower bound is 0 that when you evaluate the function there, it's going to be 0. That's true for polynomials. It's true for some other functions, but not always. It should be minus a negative, so that should be plus. Thanks. Okay, so what do you end up with? Well, the square root of 2 plus the square root of 2, half a square root of 2 plus half square root of 2 is a full square root of 2, so you get 2 times the square root of 2 minus 2, which is 2 times the square root of 2 minus 1. And if we go back up, looks like E is the right answer. And you guys are pretty smart. You wouldn't make it into BYU if you wouldn't. A lot of you were changing answers as we went along. So nice job. Emily, do you want to come? Oh, wait, I can probably stop this remote control. Not on this one. Sometimes I will, but yeah, mainly these will be just for practice, for talking through, and this is how we take attendance. Yes?
Following why we don't include, it almost looks like a triangle. It's the portion that's between the 2 shaded sides.
All right. So let me go down here. Okay. So yeah, there's this area here. Maybe. Yeah, you're wondering like, oh, come on. Yeah, you're like, why not that area, right? So that area isn't bounded by the curves or that we listed. So it's not like captured between those. If we said cosine of x, sine of x, and the line y equals 0, which would be this lower bound, right, the x-axis, then we'd be talking about that. We'd also be talking about some other things because they would repeat too. But because it's not bounded by those, so for example, if you have a point here, you could just start going down as far as you wanted. It's not inside of some bounded region. So good question. Once you do about 7 or 8 of these, you start to get a handle on what they mean by the region bounded by these. Good question. Ryan or Brian.
When you're solving for the integral, you go back to where you're solving for the integral.
Yep.
I simplified my sine minus negative cosine is just like sine plus cosine, but then it didn't work here.
Right, you simplified.
So when you're evaluating your integral and you're doing anti-derivatives, you have 2 times sine of x minus negative cosine of x.
Right.
Could you not just change that to a plus?
Yep, you can, and you still should get the exact same answer. So yeah, you still should get the exact same answer. So like both of our pluses, if you look inside there, we have changed those to pluses. And you should have a minus you should have a minus right there. So okay. All right. Any questions like this before we move on to a harder one? Or any questions about areas between curves in general? The thinking, the strategy? Yes?
How do we know whether to integrate with respect to x or y?
Okay. The next problem we do, we'll bring that up in a better situation for us to better context. Nice question. So, other questions? Okay. All right. Okay, there's the next one. Go ahead and work on this. Work with your, you can work with a neighbor, get together. If you've got questions, raise your hand. We have TAs around. So, and I'm around. So, take a few minutes.
Yeah. This area, yeah, this area. So did you put white?
Yeah, so what I'm guessing is another two, we do this minus that, and then, sorry, here one, more than two. Oh, we don't think of it. Because the integral of this,
Yeah, because there was. Is that okay? Okay.
well, no, so,
Yeah. Yeah, I just.
oh, that's bad.
Yeah, it's like getting one area.
Oh, we're so except there's
All right, I've graphed the three up here if you haven't seen it. Hope you want. All right, take 20 more seconds. All right. Okay. How many of you, you don't have to answer this question, you don't, but raise your hand if you integrated with respect to y, or you were trying to. Okay. Raise your hand if you integrated with respect to x. Okay. You. Good. Or try. Yeah. If you were trying one way or the other, it was. So this is a problem. This is a question. This is a problem where you can think about it both ways, and there's some advantages and some disadvantages. Okay. So when you think about integrating, you're thinking about how am I slicing up the area. Okay. I'm going to think about this in terms of, we'll do it in terms of x first. Okay. Fewer of you did that, but we did it in terms of x in our last problem. So when we think about x values, we're thinking about how are we slicing up these. We're going to be slicing up along the x-axis like this. And at each one of those slices, we're thinking about a rectangle. Okay? So I need to think about what are the heights and the widths of each of those rectangles. If I do that, I see that in this area over here, I have an upper function that's the red function. What is that? X equals y to the fourth. But on this other side, I have a different function as my upper function. So if I choose to do x's, I have to break this up into two different integrals, which is fine. It's just fine. A lot of people they're much more comfortable integrating with respect to x's. I was when I was in your shoes, so I would have done it in terms of x and done a couple two integrals. We do need to figure out what this point is right there. Oops, right there. It's 1, 1. You can go ahead and equate your x's, for example, here to here. You get y to the fourth equals 2 minus y squared, and then you can solve for y and factor down and stuff to find that. I know some of you couldn't do that right now, but there's a good chance to go and review or talk to your TA afterwards and say, hey, how did they solve for that equation? So you're supposed to be able to know it, but I know that doesn't mean you all do. Okay, so what would my first integral be? So what are all of the x values? I'm just focusing on this part underneath the red over here, between the red and the blue. What are all of my x coordinates that I'm accumulating area? All my x coordinates go from x equals 0 to x equals 1. So here, all of those x coordinates where I'm accumulating area is x equals 0 to x equals 1. And what's my upper function? The upper function is y. I have to solve for y, don't I? So y equals the fourth root of x, or x to the 1/4. So dx. Dx, because I'm integrating with respect to x. It's my small width there, and then I have to think about the other side between the green and the blue. So I get I go from x equals 1 all the way up to x equals 2. Those are all of the coordinates. Those are all of the x coordinates where I'm accumulating area. Oh, came back. So x equals 1 to x equals 2. Okay, it's right there. And what's my upper function? square root of 2 minus x dx. Okay, and I need it in terms of x's. My inputs better be in terms of x's here, because this is going to be my height. This is going to be my width. Okay, so I have a height times a width. So that is in terms of x's. Any question about that? If you do it in terms of x's, which I know fewer of you did. What's the disadvantage of doing it this way? Two integrals. Okay. Sorry, what? Okay. Okay. All right. So what about in terms of y? Come on, guy. I'm going to quickly create another graph here. It doesn't look nearly as good. But if I think about it in terms of y, then I'm slicing up this way. This is going to be y equals 1, because this is still 1, 1. I should have picked a better example where both bounds weren't 1, but the way it worked out. So I can think about rectangles this way. And in that case, my width is going to be, I'm trying to zoom in a little bit here. My width is going to be a dy, or a delta y. The length now, or the height, except sideways, so we can call it length. The length of those, I'm going to have to calculate, because with this distance, I can get the total distance from one of my curves, and then I can get the smaller distance from my other curve. Okay, and I have to subtract those. So my green one up there, that is the square root of 2 minus x. So the square root of 2 minus x, that would be my upper function, but I'm not doing it in terms of x. I'm slicing in terms of y. So I need that in terms of y, which we did up here again already. What did we get? X equals 2 minus y squared. And is that my upper function or my lower function? I put it close to the integral sign, so it had to be my upper. But yeah, it's the upper function because that's going to have a higher value. The distance from the y-axis up to there is a larger value than the distance from the y-axis up over to this one. So that's going to be my upper. It's further to the right on the number line, so it's more positive than the other one. So 2 minus y squared minus, what's my small distance over there? Y to the 4th dy. So together, those give me the height or the length of any of these rectangles. The distance from the x-axis over to the top part or to the right part of my rectangle is 2 minus y squared, and then I have to subtract the distance from the y-axis to the y to the 4th part, that little piece. And what are my bounds? What are all the y coordinates where I'm accumulating area? It's a nice way to think about bounds. So all of my y coordinates, I'm going to go from y equals 0 all the way up to y equals 1. Okay. All right. We're not going to go through and actually calculate this. I believe it turns out to be 22/15. You should get it both ways. So, all right. We're going to do a quick eye clicker. This is just for fun. If you don't have it out, you don't have to. But I know you're wondering what this has to do with. Let me get this done. Okay. So how much money does an individual need to earn in a year to be in the top 1% of income earners in the world? The closest estimate is. Now you might take the largest and say, well, that guarantees you, only for the cutoff, right? So what's kind of the least amount you can earn and still be in the top 1% of the world? These are in U.S. dollars; they're not in pesos or lira. Okay, so $5,000, $50,000, $500,000, $5 million, $500 million. So just take 20 more seconds. All right, we're getting not very many A's, a few E's, 7% E's, about evenly distributed between B, C, and D. Okay. The answer, when I first got this data, it was probably close to 10 years ago, so it's a little old now, but it was less than $50,000. So if you were $50,000, you were in the top 1% of income in the world. It might be a little, you probably have to earn a little bit more. To be in the top 10%, it was 25 grand. To be in the top 15%, it was $2,500. So if you weren't $2,500 in the top 15% of income in the world, that doesn't include other forms of income like subsistence farming or grow their own food, some sort of resource. Anyway, so why do I bring this up? One of the applications of areas between curves is to measure inequality. So how many of you have ever heard of the Gini index? G-I-N-I-N-Y. Okay, so an Italian sociologist, philosopher, had this idea of how to measure inequality across the distribution. And it was kind of a difficult problem. But he came up with this graph that has to do with the ideal distribution and then the distribution that you care about. So in an ideal distribution, if everyone had exactly the same income, then the percentile, so if you went like to the 25th percentile of people, they would have 25% of the income. 50% of the 50th percentile would have 50% of the income. 100% would have 100% of the income. Well, 100%, you always have 100% of the income by the time you get to 100%, right? But most distributions are not equal. So what you do is you line up people from the least income to the most income, and then you look at their percentile. So in this particular case, you might have a 50% of the income. You have, it looks like, what is that, maybe 15% of the, right, 50%, the 50th percentile, the median person would, up until then, for the lower half of the people, would only have 15%. It's cumulative. So even if you're here, like the bottom, maybe 95%, the bottom 95th percentile only has about a third of the. So Jeannie's idea was this area somehow represents inequality. The closer you are to this line, it would be more ideal. So the way you calculate a Gini index is you do the best you can to find this area, and then you double it. Why do you double it? Because the worst case scenario is you would end up with half. If this is 1, you think about that 100%, and this is 100%. And who wants a scale that goes from 0 to half, and you have a scale that goes from 0 to 1. And so you can double it. I did this for the world income. So what does the distribution look like? In terms of world income, the blue line is what the cumulative world income looks like. So you're over here at about 90th percentile. The bottom 90th percentile, their income is about 16 or 17. of the total income. We'll see both over here. And this curve is an estimate. This is x to the 17th. And we're not going to have time to actually use that to calculate the Gini index. But the area, it doesn't match perfectly, but we missed some area here and we missed some area here, but those areas are about the same. So you can actually use the orange x to the 17th to actually calculate the Gini index. So we don't have time. And weirdly, I have actually worked on a project where we were looking at NCAA football playoff scenarios and parity in NCAA football, and we actually used the Gini index to calculate parity estimates. And so, and we won't have time to talk about the details, but one of the, a high number is bad, a low number is better. And the variation from year to year is huge when it comes to parity for NCAA football. Sometimes you just have one or two people that have any shot of winning an extra championship. Other years, like 2007, there were basically seven teams that were equal that were vying for it. Anyway, have a great day. So, question is, what is parity? Parity is how equal things are. Thank you. You're welcome. Have a great day. Study for a bit. How about you? Yeah?
I don't have my iClicker yet, so I couldn't check in.